Greetings, everyone. Thank you for joining us at Exchanging Ideas 64. I'm Kanishwaran Govindasamy, the founder of Global 5G Evolution. A warm welcome to all the speakers all around the globe to make it today. To the audience there, please take a couple of seconds to click the subscribe button on top of our YouTube channel. I'll be presenting on the topic titled on the opportunities and challenges of 5G NTN. The question that arises is, can we realize a fully space-based mobile telco by 2040? Realizing a fully space-based mobile telco is technologically feasible due to significant advances in LEO and MEO satellite constellations, such as Starlink, OneWeb, and Amazon Kuiper, that enable high-capacity, low-latency global internet. The rapid development of inter-satellite links will facilitate satellite mesh networks, reducing dependence on terrestrial gateways. While HAPS and UAVs could improve coverage and latency, they may become less critical as satellite technology matures. Challenges include mitigating the geo-satellite latency, managing the high cost of satellite deployment and operation, navigating the complex regulatory frameworks, adapting ground user equipment for direct satellite connection, and ensuring space-based networks can support 5G, 6G bandwidth and large user volumes. To the speakers, would you mind to mute yourself? Although initial rollouts will likely involve hybrid networks that integrate terrestrial infrastructure, a fully space-based mobile network capable of delivering global coverage, including the rural and remote areas, is achievable by 2040, provided the technical, economic, and regulatory challenges are successfully addressed. Now, this is quite interesting, a comparison of two architectural approach for satellite-based 5G networks. We can see on the left-hand side, the transparent bandpipe satellite or HAPS is a simpler, can have the higher latency and less flexibility because all signal processing happening on the ground. The right side is onboard processors regenerative, which allows more advanced functions on the satellite, improving latency, spectral efficiency, and network flexibility. The regenerative approach is more complex but offers performance and architectural benefits for future space-based mobile networks. Now, in conclusion, regenerative payloads provide greater flexibility, better performance through advanced functions like resource coordination and routing, lower latency, and increased resiliency. However, this comes at the cost of higher complexity, power consumption, expense, and more limited upgradability compared to the transparent payloads. Um, the multiple existing and planned NTN deployments by various partners use 3GPP compliant IoT networks, primarily in MSS S-band and L or S-bands to enable the IoT and D2D communications via satellite spectrum. This demonstrates a clear industry trend towards the leveraging satellite-based IoT NTN solutions, which includes the narrowband IoT and NTN new radio for use cases such as IoT, D2D, SMS, and image transmission, with a growing ecosystem of partners and devices supporting these capabilities across different orbits. Overall, the table shows the practical development and deployment of satellite integrated IoT networks consistent with the 3GPP standards. Now, this is a D2D communication using both terrestrial mobile spectrum bands and satellite spectrum with multiple existing and planned NTN deployments, which is leveraging on the 3GPP compliant technologies such as the unmodified LTE and narrowband IoT across different spectrum bands, which includes the 1900 megahertz, the sub 1 gigahertz, the MSS L band, and the SS S band. Majority industry partners like T-Mobile, AT&T, Verizon, Vodafone, Apple, and China Mobile are collaborating to deploy solutions that support messaging, voice, SMS, image data, and emergency communications as well. Now, this is quite interesting in terms of the IMT 2020 standards, which set significant higher performance requirements for terrestrial network components compared to satellite components, reflecting the different roles and capabilities of the 5G networks. Specifically, the terrestrial infrastructures demand much higher peak data rate, like 20 gigabit per second downlink and 10 GB per second uplink. And user experience data rates is about 100 megabits per second downlink and 50 megabits per second uplink to support mainly the dense urban environments and high user throughput, while satellite components have lower peak and experience data rates due to the limitation of the satellite form. So it's like 10 megabit per second per meter square, where the satellite system will focus more on broader coverage with lower capacity per area. And this shows the complementary nature of satellite and terrestrial technologies, with satellite providing the wide area coverage, terrestrial system delivering the higher capacity and throughput in dense population areas. Now, this is on the 3GBP new radio NTN specifications across the release of 17, 18, and 19 to expand and enhance the satellite and non-terrestrial mobile communications. Release 17 introduced foundational support for GEO, MEO, and LEO constellations with GNSS capable user equipment and basic spectrum bands. Release 18 builds on this deployment above 10 gigahertz, which is on KA band, improve mobility and service continuity between the different NTN segment. And the fixed VSAT support for a better satellite backhaul. Release 19 further advances this technology by incorporating regenerative payloads, enhanced downlink and uplink throughput, and also the extended frequency band, including the KU band. And the next slide is very much towards to the 3GPP IoT NTN capabilities, which are being gradually enhanced across the release 17, 18, and 19. The release 17 establishes the foundation support for specific frequency bands like the B256 and the B255, GEO LEO constellations, and the GNSS capable user equipment and transparent payloads. Release 18 improves mobility procedures, disables the HARQ feedback, introduces the discontinuous coverage, and extends the frequency band support. Release 19 focuses on advanced features such as store and forward operation on regenerative payloads, uplink capacity enhancements, support for higher transmission power in selected FR1 bands, and the new band combinations and introduction of the S band, which is the B252. And lastly, the ecosystem for satellite and NTN-based mobile telecommunications involves multiple vendor segments, space segment, ground segment, user terminal segment, and applications, and working together through a layered architecture. And satellite services like D2D, broadband, IoT, and satellite-capable user terminals like the NTN-enabled smartphones or VSAT devices are delivered via a combination of space-based vendors and product service providers like the SNO, MNO, seller, and user terminals. And these are the applications leveraging satellite connectivity are also very important to the ecosystem. And the framework highlights that service delivery to end users is a coordinated process involving payload and satellite bus vendors, ground gateways, terminal operating system and chipset vendors, and application providers, and illustrating the complexity and interconnectedness required for a functioning NTN enabled mobile network. I think that's overall the presentation from my side. And I would like to, just one second, introduce our next speaker, Eric Davidson from London, UK, to present on LoRaWAN and 5G NTN complementary technologies for a fully connected planet. Over to you, Eric.
Thank you, Ganesh. Really appreciate the opportunity to talk today. Let me just see if I can pull up some slides. Okay, can we see that?
Yes.
All right, thank you very much. So obviously today's the main topic of discussion is 5G NTN. I'm Eric Hewitts, and I'm a business development manager at Lacuna Space, based in London. As Kanesh said, we're also partly based in the Netherlands. So we're yeah, we have two main offices there, one in each country. Lacuna Space are somewhat outside the 5G part, but it will be an interesting sort of start to the day to just place what's going on outside of that and what's going on right now as well in terms of connectivity as the 5G net end-to-end sort of environment begins to grow over the next few years, or continues to grow over the next few years. So Lacuna Space, we're based in, as I said, in the UK. This is a UK centre. We're at the Harwell Space Campus, which is just outside Oxford, and this is the sort of centre of the UK space industry. And we are very much a low Earth orbiting satellite operator. So our constellation is low Earth orbiting satellites at about 600 kilometers in orbit. We also have an S-band operation as well, which is in the MEO sector, so in that sort of mid space between the LEO and the GEO. And we'll come on to that in a bit. But our SAS satellites are launched by SpaceX. This is the Transporter 14 that went up last month with 2 of our satellites on board. And we've got 4 more going up with SpaceX in the autumn, in October. And when they're launched, as I said, they're at 600 kilometers up. They're traveling at about 25,000 kilometers an hour. They're rotating around the Earth every 90 or so minutes. So doing multiple orbits each day, and as the Earth rotates around underneath, then at some point or other, even with one satellite, you're going to be overhead and able to connect data from sensors on the ground. And obviously, the more of a constellation you build up, then the more opportunities you get to send data, and the more data you can send overall. But this is very much in the Lacuna Space operate very much in the world of low data. So we're talking 50-byte messages a few times per day. So this is very much for those small sensor operations. What's the temperature? What's the flow? What's the pressure? Where am I? What am I on or off? Those kinds of values. And that's a visualization of what it looks like from space. Here's a satellite with the antenna extended as well. And IoT Analytics, German information company, have looked at the satellite IoT market in general, and their projected growth of 26% per year, year on year. And we're certainly seeing that from our competitors and from ourselves as well, that's the kind of growth we're looking at. Now, I've sort of tried to make this grand claim that if you're operating these low Earth orbiting satellites, you've got global coverage, and absolutely you can, but there are, of course, some political considerations to take into account, and that is the fact that even when, like us, you're operating in the unlicensed spectrum, so Lacuna Space operates in the 868.915 bandwidths, so that's the LoRaWAN spectrum. That's unlicensed, so we don't have to pay anybody for the license to use that bandwidth, but you still have to get an agreement from country by country in order to operate within those countries. Some countries, like a lot of the countries in the Middle East, are very particular about only allowing you to have a ground station in country, so they don't like the data to be coming outside of the country or to have to rely on ground stations in other places. That's not super convenient for low Earth orbiting satellite operators, because it's much easier to have ground stations at the poles or near to the poles, where satellites will pass overhead more frequently because of the convergence of the lines of longitude. But this is just the nature of how the world is right now. The European Union or Europe collectively has agreed to the use of satellite with the LoRaWAN spectrum. So that's we hope will trigger more licenses going across the world as people realize there is a huge upside to having this capability for multiple industries. I would say primarily Lacuna Space and a number of our competitors are working in several key verticals: agriculture, environmental monitoring, the blue economy, remote energy and utilities infrastructure. And there are others, but those are key ones, certainly for Lacuna Space. And that's because these are the industries that have many assets that are located outside of the cellular range, outside of the sort of 15 or 20% of the Earth's surface that has cellular coverage. So we're going after that 80% of the Earth where there isn't cellular coverage, where there's currently, it's very difficult sometimes to get any data out without having to go and visit sites, which is expensive, without having to have, you know, super powerful big satellite dish going with some of the bigger satellite operators, where you may struggle to find the power, or it's certainly going to not be cost effective if you're trying to get certain types of data. So what does the ecosystem look like? Well, essentially, we're talking here about the world of sensors on the one hand, and of data analytics platforms on the other hand. End users really are only interested in the benefits that are derived from the data that they can see. They're not even interested in the analytics platforms themselves. They are interested in the results that come on the back of that. So on the left-hand side, you've got sensors. So we work with multiple sensor manufacturers, as many satellite operators are going to do. They're going to work to either attach a sensor to a device that can speak to the satellites, or embed that technology within the sensor if there's enough volume for them to do. We work in the LoRaWAN spectrum. So of course, LoRaWAN is from an IoT perspective, it's about 40% or so of the overall IoT market, and it's very much the preferred protocol for remote location connectivity terrestrially. But it does require having terrestrial gateways. It does require, there are issues around power for gateways, the cost of infrastructure of putting in gateways, and that satellite connectivity solves that problem. But the two working together can be very, very powerful. So if you can reach a terrestrial gateway, you use it. If you get moved away, then you can jump onto the satellite. We have a network management system where you onboard your devices, where everything's managed. You can see future, you can see orbits of satellites, so you can predict when you're going to get your next data, that sort of thing. Lots of different functionality, but ultimately it's an API into a data analytics platform. So this is Lacuna's multi-node, which is our standard device that you can connect a sensor to. So that's SDI 12 RS485 connections into this box. As long as you're facing the sky, you do need to have visibility of the sky. Then you can get data sent, even on very low power, with solar backup, of course, as well. You can basically run indefinitely. So just something quickly on the coverage issue, just reiterating what I was saying about the local area network created by a LoRaWAN gateway on the ground. You might get sort of 10, maybe if you're lucky, 20 kilometers. But if you go outside of that, then you've got to have another gateway. And of course, your gateways have to be powered as well. So that gives you that issue. But with the satellite network, you're basically free from that. You've freed yourself up from having to spend more money on infrastructure. So this is very much a solution that currently solves that problem of remote connectivity. When 5G gets more developed and becomes more mature, there's still going to probably be use cases where it just doesn't make sense, because this is such a cheap, such a low cost, such a low powered solution, that there may still be use cases that the 5G can't have. So I think there's a complementary side to 5G NTN and the LoRaWAN connectivity to space. This is a diagram from the LoRa Alliance, obviously a big organization that manages the LoRaWAN ecosystem, with lots of members, and great work's done there. This is just showing some of the many different types of sensors that exist around agriculture. And then finally, just a few screenshots of just some deployments to make it a little bit real. So these are weather stations, soil moisture sensors, power connections. The one on the bottom left is a peat moorland in the north of the UK, where we're looking at sort of water retention in the peatland moors. And that's it. That's it from me. So thanks very much for listening. I do appreciate it.
Awesome, Eric. Thank you so much. I really appreciate that. And now let me introduce our next speaker, Mikhail Glukovchenko from Moscow, Russia, to present how to build terminal for Leo. Over to you.
Okay, I will try to share. Okay, hello everyone.
Are you able to share a slide?
Yes, I will try. Okay. Hello everyone. Yes, hello everyone.
Yes, please continue.
Okay. Okay.